Alright, so let's do a couple more examples with partial fractions. So suppose we want to find the inverse Laplace transform of the fraction 3s plus 19 over s squared plus 6s plus 34. First thing we notice is this thing. In the denominator, it doesn't factor because it does not have real roots. So we need to instead, as we have to complete the square. So s squared plus 6s, the middle term is 6, divided by 2, which is 3, and we square 3, which is 9. So 9 is the number that's needed to complete the square, and 34 minus 9 is 25. And this is equal to s plus 3 squared plus 5 squared. So that means the original fraction is equal to 3s plus 19 over s plus 3 squared plus 5 squared. Since we want to find the inverse Laplace transform of this, it suggests that cosine and sine here are being used to find the inverse Laplace transform. So we need to figure out how many cosine there are and how many sine there are. So we assume this is equal to a times s plus 3 over s plus 3 squared plus 5 squared plus b times 5 over s plus 3 squared plus 5 squared. So in both of these cases, a is negative 3 and b is 5. Okay, this is not hard to solve. We compare all the denominators and numerators together. We get as plus 3a plus 5b is 3s plus 19. Compare the coefficients, we get a equal to 3, and 3a plus 5b is 19, which tells us that b is 2. So that means original fraction is equal to 3 times s plus 3 over s plus 3 squared plus 5 squared plus 2 times 5 over s plus 3 squared plus 5 squared. So the inverse Laplace transform of the original fraction is the inverse Laplace transform of a new one, which is equal to 3 and 2 are staying, and looking at the chart, it's equal to e to the negative 3t times cosine 5t and e to the negative 3t times sine 5t. Alright, so let's look at more complicated examples with combined cases. So let's suppose we want to find the inverse Laplace transform of s squared minus s plus 1. The denominator is factor for you, so suppose we have s squared times s squared plus 1. Okay, so the denominator is always factor for us. So using the method of partial fraction, we can assume the original fraction is equal to, so s squared is the duplicated factor, so we have a over s and b over s squared for the duplicating factors. And s squared plus 1 is the quadratic factor that does not further factor, so we have cx plus d over s squared plus 1. And same trick, we first multiply by the common denominator, so we get s squared minus s plus 1 equals to a s plus squared plus 1 plus b times s squared plus 1 plus cs plus d times s squared. And same thing, we're plugging roots. So one of the roots is 0. So first we plug in s equal to 0. Then we get 1 equals to b. Everything else went away, which is nice. We can also plug in another root, which is the root for s squared plus 1 equal to 0, which is s equal to I. Then we get I squared minus I plus 1 equals to The first and second term are 0 because s squared plus 1 is 0. And we have ci plus d times I squared. I squared, recall, is -1, so the left-hand side is -I. The right-hand side is minus ci minus d. And because this is a quality of complex numbers and c and d are real numbers, so we can just compare the coefficients of I and the constant part. So we get -I equals to -ci, and 0, the real part, is equal to -d. So this tells us that c is equal to 1 and d is equal to 0. Okay, to find out what b is, it's a little more complicated. We need to first take the derivative. So let's do that. So we get 2s minus 1 equals to, for a, we have to use the product rule. Sorry, I meant to find out what a is. It's more complicated, not b. So we use the product rule. We get a times s squared plus 1 plus a times s times 2s, and then plus b times 2s plus c times s squared, product rule again, plus cs plus d times 2s. You notice that every single term except the first term has s in it, so we plug in s equal to 0. And we get -1 equals to 8. Everything else went away when we plug in s equal to 0. Alright, so that means the original fraction is equal to -1. -1 times 1 over s, that's a, plus 1 over s squared, which is b, plus c is 1, d is 0, over s squared plus 1. And the inverse Laplace transform of the original fraction is the inverse Laplace transform of all these terms together. Inverse Laplace transform for -1 over s is -1. N equal to 0, a equal to 0. And for the second one, n equal to 1, a equal to 0. So s, this is t. For the third one, it's s over s squared plus 1. That's cosine. So this is just cosine 1t, not shifted. So this is our final answer.